Hello everyone. Today I'm going to discuss about the synthesis of methohexital sodium. So we all know that methohexital is an example of intravenous general anesthetic, and it is also going to reduce the threshold of seizures. Okay, so coming to the synthesis of methohexital sodium. So the starting material will be diethyl malonate. Which reacts with 3-bromopropene. Right. So we all know that when 3-bromopropene reacts with diethyl malonate, what happens? Initially, the bond present between the carbon and bromine will break. Okay, so as bromine is having more electronegativity, okay, the electrons will migrate towards the bromine atom and it will get negative charge. Okay, similarly, carbon and hydrogens are there here. Okay, when you compare the electronegativities, carbon will have slightly more electronegativity than hydrogen. So hydrogen gets positive charge. So positively charged hydrogen and negatively charged bromine combines to liberate HBr as a byproduct. Okay, so another reason for getting positive charge on hydrogen is due to the presence of the 2 electron withdrawing carbonyl groups, ketone groups. Okay, so these ketone groups will enhance the acidity of hydrogen atom. Therefore, hydrogen atom loses its bond strength and it will get a positive charge. Okay, this is how HBr is liberated as a byproduct. Okay, so when hydrogen leaves the reaction, here carbon will get lone pair of electrons, and here when bromine leaves the reaction, carbon will get positive charge because bromine is highly electronegative. So the adjacent carbon will become electron deficient. So what happens is as carbon is having positive charge, this carbon atom will transfer the electrons to the positively charged carbon atom here. Therefore, a new sigma bond will be formed between the 2 carbon atoms of 3-bromopropene and diethyl malonate. So you can write the intermediate compound in this way, C double bond O. Okay. Next, C2H5 oxygen, and here also C double bond O, C2H5 oxygen. Okay, and here you will get CH plus, this is a new sigma bond formation between this carbon and this one. CH2, CH, double bond, CH2. This group you can call it as allyl group, ALLYL, allyl group. Okay, so this is one intermediate compound you got here. So this intermediate compound you can react with another substance. This is called as 2-bromo-3-hexane. 2-bromo-3-hexane. Right. So here there is hydrogen will get positive charge because of the difference in electronegativity, and here bromine will leave the reaction with a negative charge. Why? Because if you break the bond between carbon and bromine, electrons will migrate towards bromine, therefore it gets negative charge. Okay, therefore this carbon atom will get positive. And here the lone pair of electrons will be there with carbon. Okay, so this hydrogen and bromine combines together to liberate another molecule of HBr. So you can write the intermediate compound again, C2H5O, C double bond O. Okay, next again, C double bond O, C2H5 oxygen. Next, you are having one allyl group, right? CH2, CH, double bond, CH2. And here also, so before that, you'll be having one bond with carbon, right? So this carbon will bond with CH, CH3, next C triple bond C, CH2, CH3. Okay, this is one intermediate compound you got here. Okay, so this C2H5 C double bond O, C2H5 C double bond O is common. Again, you are having this carbon atom here, the same carbon atom I have written here, followed by CH, CH3, C triple bond C, CH2, CH3. So this portion I have written the same once again here. At the same time, you are also having this allyl group. So this allyl group I have substituted at this position. Okay. Now, the last step is nothing but cyclization reaction. So this cyclization takes place in the presence of N-methyl urea. So this is N-methyl urea. Okay, so you can write here C, this one I'm writing C double single bond CH, CH3, C triple bond C, CH2, CH3. This portion I have written the same, followed by allyl group CH2, CH double bond CH2. Up to this portion, I have written the same thing in the final structure also. So this portion I have written once again here. Okay, then what will you get now? You are having this C double bond O. So you can write C double bond O. Okay, followed by this one, NCH3. Okay, NCH3. This NCH3 you are going to get from N-methyl urea. Okay, followed by again one more nitrogen, followed by the ketone group. Okay, and here you will get sodium salt, NaO. So this is a structure of methohexital sodium. Okay, so this allyl group and this hexyne substituent you are going to get from the previous intermediate compound. Only thing I have done is I have converted this acyclic structure into a cyclic structure in the presence of N-methyl urea, which is a powerful cyclization agent. So this NCH3 I have written here, okay, followed by the sodium salt, NaO, you are going to get from sodium hydroxide. Okay, so this is a strong base we are using here. So this sodium hydroxide, okay, when you break the bond between oxygen and hydrogen, you will get H plus and NaO. So this NaO I'm going to substitute here. Okay, so this hydrogen, okay, and another hydrogen atom from N-methyl group and one oxygen. This will be removed in the form of a water molecule, so that you are going to get methohexital sodium. Look at here. NCH3 I have written here, followed by NaO. NaO you are going to get from sodium hydroxide, followed by another nitrogen. This nitrogen you are going to get from N-methylurea, this nitrogen. So here two hydrogens are left over. Okay, so it can be removed in the form of a hydrogen gas also. Okay, so you can get this product called as methohexital sodium. This is about the synthesis of methohexital sodium. Thank you.